Normally, in this part, people would basically start doing their own problems or trying to do the challenges on their own, and we would just basically walk around the room and help everybody one by one. But it's kind of hard, given the conditions, to do that. So what I'm going to try to do is I'm just basically going to take the first challenge and try to solve it. So I have here the slide, basically where I describe the challenge in my talk, and I just realized that I have a typo here. What I said is I suggested CR203, but all the data that I put was for CR03. So please disregard this little typo that I have here and just do the problem for CR03 and not CR203. So let's just review what we plan to do. We just basically try to find CR03 in web atoms. We are not going to run the LDOS. We are just trying to do the K-edge of chromium in that case. We're going to set up the convergence to basically use this number of shells, more or less. And we're going to visualize the results and see if we can find some results in Google Scholar, for example. Actually, I'm just probably going to go and look at the PDFs just to accelerate things in this particular case. So I have web atoms here, and what we're going to do is we're going to go to their database of atoms.imp, and we're going to look at chromium here. And although there is CR203, we're going to go and look at the trioxide, and we're going to run web atoms. Like I said before, you have to choose the FEFF, and we're going to do it by sites. I'm going to choose a radius, like I suggested, a large one of 11. And we are going to do a K-edge. So everyone that seems to be set up properly. The absorber is on the chromium. Let's compute and see what we get. So this seems fairly reasonable. K-edge, you have all this set up properly. There's a certain SEF radius set up here, but we're going to be adjusting that properly in a little bit. Let's see. The FMS is not set because this is trying to do basically setting up for doing an XAS calculation, but we're going to change that. You can see everything seems to be reasonable in the FEFF.imp. So what I'm going to do is I'm going to save this. Hopefully everything is okay. I'm saving it to my computer. And what I'm going to do now is I'm going to go to my downloads and take that FEFF.imp, and I'm going to put it in this area that I created. I created like a teaching playground area that I mentioned in the email. And inside there's a challenge one, and there's a folder called hands-on. You should be able to actually see all this in the Google Drive. If you have the Google Drive folder open, you should be able to be following the files that I'm basically modifying and loading and doing everything with here. So I also have FEFF here already started. I mean, you just need to basically bring it up. And I'm going to try to load that FEFF.imp that I just generated. So we're going to come here. We're going to say open. And I'm already in the teaching playground area. I'm going to go challenge 01, hands-on, and there's a FEFF.imp. I'm going to open it. And if you see here, like I mentioned, it is set up to do an XAS calculation, and it has some certain radii in there. Let's visualize what we have. Nice chromium trioxide. You can see the structure that it has. There you have the chromium, and it has some nice 3 oxygens around it. So we're going to take a look at the atoms. Edit here, and see if we can calculate more or less what 4 shells corresponds to. If you look here, you see more or less the distribution of atoms. And you can see that the 4 shells would be maybe 1, 2, 3, 4, something up to like maybe 3 angstroms or so, 3.25 angstroms. So we are going to change the SEF radius to, I'm going to close here for a second. I'm going to change it to 3.5. And we're going to change here the spectroscopy to SANES. And we're going to change the FMS radius to, let's look again here. Let's count a little bit more. There's like 1, 2, 3, 4, 5, 6, 7. Yeah. Let's go to about 5.9 or so. So, like I said, you don't want to run the LDOS. We're just going to do final state rule. And with these settings, the calculation should take a little bit of time. It's going to depend enormously on if you're following this, it's going to depend enormously on the machine that you're running with. My machine is reasonably fast, so hopefully it's not going to take too long. Oh, so we say save and run. And if I did not forget anything, this should run properly. Something is very close, but hopefully it's not going to be too much of a problem. Oh, great. Amazing. Of course it failed. What did I do wrong? See, this is what happens every time I try to do stuff. Josh, do you have any suggestions? Let's take a look.
I was busy answering a question when I saw when the system went by. What system is this?
CR03.
CR03?
Yes.
And you just produced this using WebAtoms just now?
Yeah, just now.
Okay. So it's saying that 2 atoms are very close together.
Yeah,
I would guess this has to, so atoms sometimes has to have a particular shift. And it will
yes, you're right.
At the top of the input file.
Yeah.
So if you go back to atoms.
Let's try it again, as usual. Let's go back.
Let's see if it warns anything there.
Doesn't seem to have anything fantastically weird about it.
Maybe I'll try doing the same.
Yeah, you should probably try. So I think this is probably a good example of what the kind of things that you are going to be finding as challenges in this type of problems. I'm surprised that they are closed.
So I am having trouble getting into WebAtoms.
Oh, okay. So I'm not looking at the chat right now to see if people are actually maybe mentioning that they are having trouble with it.
Is anyone else having trouble getting into WebAtoms?
I can't look at the chat really.
I've been there 5 minutes ago and it worked fine. I can try again.
Okay. It seems to be working for me too. So let me just try something very quickly. Let me try loading the file that I previously generated for this. So I do have an input file for it that I pre-generated So you can find it in this other directory. If you go to the challenge directory, I have a hands-on folder, but they also have this other one that has an input in there. Let's load this one and see if this one works. Okay, so this one is already set up with an SEF of 4, an FMS of how much? How much is it? 5, so that's all reasonable.
I
So let's
just
save and
suggest to
run.
compare the structure you have in the saved file with the structure you
Yeah,
took
so
from
this
FEFF.
one works perfectly fine. So there might be a difference in the setup because this was actually the original files were generated with an older version of WebAtoms. So let me just see if I can be absolutely certain that I'm using the right thing. For now, you just don't need to use the ones that you generate from WebAtoms. You can just use the one that has been provided. So yeah, so this was done with the 1.8 version of WebAtoms. Yeah. Anyway, so good thing this one actually run properly. So if you can see here, I mean, you can see the SEF running, 1 iteration, 2, 3, 4, 5, and it's done in 12 iterations. Like I showed you before, you have the charge transfers, and then it goes and does the FMS, all the points in the FMS, and so on, and finally calculates the XAS. So now, if you just say plot, we should be able to have a spectrum in here. I'm going to make the colors again darker so you don't have a problem like we had before. So I hope you're seeing the result. It's fairly nice and clean. And in here, I have 2 PDFs of with results. So let's open both of them, and we can do a very rough comparison of the results. So this is Chromium, and here we go. So let's look at the pink curve that you have here in this particular case, and let's look at the result that we got. You have a very clear peak. The intensities are a little bit different, but that might be related to the way that we are setting up our cutoffs and everything, but you kind of have the right structure in the spectrum. This is like a first approximation, obviously. Let's look at the other result that was published. It's this one. Let's see if they have a CRO 203. That's CR203. Yeah. Now this one has CR203. Where is this? I know they have it somewhere. Here we go. So this is CR03. Again, you have this case. It seems to have an intensity of the white line of this peak, white line peak, to be significantly lower than what we are calculating with FEFF. But there's always room for improvement when you do FEFF calculations. So let's see if we can run it again with a slightly larger radii. Let's go with 6. And this one, let's do it 5. Let's go with 7. Hopefully it's not such a long calculation. It is actually running at a reasonable speed. It's not super fast, so it's going to take a little bit longer. So this is the kind of things that you should always do. So you run your calculation and using some simple settings in the beginning, and then you do and improve your settings to try to find convergence. Ideally, what you would be doing is you would be saving this in individual folders. You would be basically having different folders for each one of the calculations that you're doing, and then you can go and plot the calculations that you did one on top of the other, and seeing if you have reached convergence. That's the typical procedure that you would follow. This is getting closer to convergence. Yes, pretty good. I'm just trying to see if I can get something better to do the comparison right now. Do you want to add anything, Josh, while I wait for this? Am I forgetting anything?
I was actually just looking into seeing if I can find a different crystal structure for CR03 from that we can input into WebAtoms.
Oh, okay.
So basically, it looks to me like the crystal structure that's in there is not correct. So the WebAtoms database is not curated, so you always have to be a little careful about,
Yes.
Hopefully most of them are right, but that one seems to be incorrect.
Which is kind of surprising because, I mean, at some point I did generate it. So, yeah, it is kind of weird.
I mean, it could be that there was some update as well that changed it.
Yeah.
But there are clearly atoms that are, like, if you look at the first couple atoms in there, there are two that are about 0.3 angstroms apart. So the second and fourth atom, for example,
yeah, I can tell
are
immediately.
clearly not correct. You can't have.
Yes, those are not. Yep. Yeah, definitely not.
So anytime
this is pretty...
FEFF gives that kind of warning, that's definitely an indication that your structure is right.
Yep.
Sometimes when you have hydrogens in there,
that is a very typical case. Yes.
And that's a typical case where your structure isn't wrong, but you still get that warning. But otherwise,
okay, so you can see that the calculation finished. So we're going to plot again and see what happened. Okay, so things are actually getting better now. You can see that the intensity is significantly lower. You still have a little bit more broadening in certain areas, but it does look a little bit closer to what the experiment was showing. So you can definitely see that it's working reasonably better. You also have to compare the energies and the energy ranges. In this case, this is a very broad energy range. We are going like up to like 250 eV above the edge, more or less. And here in the plot, we are only going to maybe 130. So we should be basically seeing just this chunk over here. If you want to expand the range, I'm going to try to expand the range and rerun the calculation. You can change the K limit here, and I'm going to change it from 6 to 8 just to go a little bit higher and just rerun again. Again, it's going to take even longer now because we are calculating a longer energy grid, so you have more points in energy points to compute. But it doesn't take that long in this in the computer, so you can actually take a look at it and see if we can maybe see the second hump here between 100 and 150, more or less above the edge. When you do this, when you go higher in K, essentially higher in energy above the edge, you have to start being careful about a few things. First is the quality of the basis set that FEFF, the L basis set that FEFF uses. If your results are not spectacular in that energy range, you might want to consider increasing your L max. This is something that I'm not going to do here because it would make the calculation significantly more expensive. The other thing that you have to start taking into consideration is the Weierwald factor effects, or essentially vibrational damping effects, which are not very noticeable near the edge. But as you get higher and higher, you have to include them. Otherwise, you have many more oscillations than you should have there because you're not including the vibrational damping. This is getting close to convergence. It's almost done. So pretty soon, yeah, there you go. The SEF completed. Now it's going to do the FMS. As you can see, the FMS is actually running fairly quickly, and it's almost done, and we have it. So now let's take a look and see if we have a broader energy range. And yep, we went above a little bit more. I didn't want to kick it down much more, but yeah, and you can actually start seeing the second pump that you have here that goes up to like 150. So, oops, sorry. Where did I go? Where did it go? Here we go. Yeah, 150, you can actually see it. And if we went even higher, you should be able to start seeing it. We can try to change the broadening a little bit to see if we can modify the calculation and make it look a little bit better. This is something that is a little bit ad hoc, if you want, but it's actually something that people do reasonably in many cases. So let me see if I can find it. I can never find it. Where is it? And, there we go. Okay, so just let me see. Let's increase this. So what I'm going to do is I'm going to add a little bit of extra broadening to the calculation, and I'm not that used usually to the FEFF GUI because I usually do these things in with the input file. So what I'm going to do is I'm going to show you how to do it here. So let's save it. Actually, let me change the this back to 6, and let's save and run again. Hopefully this one is going to show us a slightly broader calculation. So Josh, are you looking at the chat and seeing if there are any questions in there and you're answering them?
There have not been any questions in the chat so far, and the Piazza, I think, is also no questions.
Okay. So what I'm going to do is, okay, so I'm going to finish with, I'm going to basically show a little bit more of this specific calculations and running a few, just showing the extra broadening in this particular case. But then I'm probably going to see if I can move to the other example, because what I want to do is I want to try to move through the challenges rather quickly, so we can maybe leave some time later on for actually back and forth with the people, even if it's a little bit more complicated. I think they're going to probably learn a little bit more by just doing, by just asking us questions and us answering very more specific questions in particular. Don't you think that's probably better? I think I actually changed the Fermi level position in this particular one, which is still going to be a good example. Yeah. Oh, okay. There you go. So yeah, no, actually, you can actually see that I actually made the calculation a little bit broader, and the agreement now looks better. The agreement with experiment looks a little bit better because we have that little bump there that is getting close to the little inflection point that you see in the experiments here. There are small differences up here. This is probably related to the structures maybe not being identical, or maybe having some self-energy. The self-energy is not being perfect and so on. But the agreement that you're getting here is actually pretty good quality. It's a good starting point to doing your research in this case. you can actually see that, yeah, we go now to 175, so you can see that we see the whole hump in there. Ideally, what we would like to do is you would basically get this data digitized, and you would plot it simultaneously with your FEFF output, and you will get a much better idea of how good the result is. Okay, so let's see now if I can move on to the other challenge. So the idea of the other challenge was to see if we could if we could generate a model for a nanoparticle, okay? And just 19 atoms. And then what we would do is we would try to modify the input file so we can calculate the center atom, an edge atom, and a vertex atom. So what I'm going to do is I'm going to go to Web Atoms again. I'm going to select platinum, and I'm going to generate a generic input file that I'm going to be modifying in later on. So first of all, here I am in the area that I'm going to be using. Let's go back to Web Atoms. Here we go. Web Atoms interface. We're going to look for platinum. Just get platinum, run Web Atoms. We're going to do it by element because it's very simple. And if you look here, there are plenty of atoms in this one. So we're going to select a radio that is much smaller. So we are going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19. So 19 atoms, we need to cut this at about 4. So we're going to choose a cluster size of 4 and compute. And this should give us exactly what we want, a small nanoparticle of 19 atoms. And we are going to essentially save this. Okay. Let me close here. Let me go to my downloads. And we are going to move that FEFF IP here. So now what I'm going to do is I'm going to make 3 directories because we want to run different things. We want to do 3 different calculations. We're going to do a center, an edge, and how was it that I called it? The other one? Center, core, shell, and surface. Okay, let's do it that way. Actually, let's do it exactly like I said, edge and vertex, center, edge, and vertex. Okay. I'm trying to be consistent with myself here. Okay. Now what we're going to do is we're going to copy this input file into each one of these ones. It's like an initial input file. Okay. So now we have a generic input file in each one of the directory, the folders that I made. So we come back to FEFF and we are going to load. We start with the center one. We are going to go to the playground, challenge 2, hands-on, and go to the center. We're going to load it. So we're going to change this from XAS to SANES. We're going to look at the the structure, and you see that it's already in the center. The absorber is already selected in the center. And we're going to look at the structure and see what is the radius that we want to choose. So anything above 3.92 is a good radius. So we're going to choose an FMS radius of 4 and an SCF radius of 4, and that covers the whole nanoparticle. The rest is actually fairly simple. I think all the rest is essentially standard. An L3 edge, everything is fine. So let's save and run. This should run very quickly. Perfect. So we can plot it again to see. Let's change this horrendous color. And you have your result for the nanoparticle, actually for the center of the nanoparticle. This is actually quite nice. So what we're going to do now is we're going to go to the other one. We're going to open, instead of the center one, we're going to open the edge one. Okay. Wait. There we go. We're going to open the edge one. Again, change this to sains. We're going to say 4 and 4 in this case. All the rest is the same. But now what we have to do is we have to edit the structure, and we're going to change the absorber. So first you saw that the absorber was located in the center. That's why you have a potential of 0 here. So now what I'm going to do is I'm going to change it to one of this one. So I'm going to change this one to 1, and I'm going to change this one to 0. And we are going to take a look at the structure, and hopefully, oh no, edit. Why doesn't it show it? It should be showing it. Josh, any comment why it's not showing it at the edge? It should be showing it at the edge.
Let me see. What are we doing here?
Okay, we changed it, but
at the edge.
Yeah, I think we maybe
Okay.
if we save and run, it's probably going to do it. It's probably not updating.
Yeah, it hasn't saved it yet. That's one thing. The other thing that you probably want to do is make sure you save it in a new directory.
I'm already working in a different folder. Yeah. That's I made sure of that. Yeah, I talked about that.
You can also do file save, and then it probably will update.
There you go. That did it. So now you can actually see that the absorber is in an edge. So let's run this one. Good. So it's over. So we can plot it again, and you can already see that there are huge differences between having the atom in the center and having the atom on the edge. So we're going to repeat the same process with a corner. Okay, so we're going to come here. We're going to say open. We're going to go up to the vertex one. We're going to open. Again, if we view it, it's going to still be in the center. Let's change this to sains. And we're going to do it again 4 and 4. We're going to come here and edit it. And we're going to say this one is going to be 1, but we're going to choose this one. This one corresponds to the vertex. And we're going to say close. We're going to say file and view. And now we have it in one of the corner ones, not the vertices. So we can save and run. It's done. And let's plot it again. Very nice. So what I'm going to do now is I'm going to add another file. I'm going to go to the hands-on case, and I'm going to go to the center one, and I'm going to load the xmu.dat from the center one. And I am also going to go and open the one from the edge and load the xmu.dat of the edge. So let me change colors to make this a little bit more appealing. So here you have a very clear comparison of what is going on. You can actually see that even the oscillations higher up are completely different. And the edge part is the part close to the white line is completely different. You can actually make some nice comparison. If you look at the blue one, which is the one that is in the vertex, it has much lower amplitude oscillations, and that is because you have fewer neighbors. There's just like a few scatters right next to it. So the fewer scatters you have around it, the fewer, the lower amplitude your oscillations in the XFs-like region is going to be. And as you go to the one that has the red one, which was the one in the very center, is the one that has the highest amplitudes, and the one that it was on the edge, which is the green one, it also has slightly higher amplitudes because the edge has more neighbors, but it's actually kind of closer to the one that you did for the vertex. So this is a very typical thing that you would do for comparing structural disorder. So if you actually had a nanoparticle that you were going to do simulations for, you would have to take all these three calculations that you did, and you would have to do an average. And in this particular case, it would have to be a weighted average, because if you look here, you have how many atoms of the vertex type? You have 1, 2, 3, 4, 5 of the vertex type. And you would have to basically average with a weight of 4. And if you did the edges, like these ones that are here, you would have to do 1, 2, 3, 4, 5, 6, 7, 8, and 12 in total, and there would be just one center atom. So that's a typical way of doing the averaging, and there's no way to do it directly in FEFF, but you would have to do some other code to actually do your average. But so I don't know if there are any questions about this, Josh, that I can answer, because I can't see I don't think I can see the chat.
Sorry. Let's see. Well, somebody asked about whether you need to change FMS and SDF cluster sizes when you switch from the center to the vertex. And I gave an answer to that, but if you want to go ahead and talk about it.
I assume that you basically told them that in this particular case, we are using exactly the same FMS and SEF radius in all the calculations to make everything very nicely consistent. And basically, we try to encapsulate the whole nanoparticle. In that case, this is possible. If you had a system that was a nanoparticle that was larger, like in the nanometer range, you probably do have to do the same kind of tricks that you would normally do, which is test for convergence with respect to FMS and SCF radius. In this case, we don't have to, because we can just encapsulate the whole system in one set of SCF and FMS radii. You saw me set it to 4, right? Which is, if you look at the structure that we have, it encapsulates all the atoms that you have in there. If you want to be totally absolutely safe, this is the distance from the absorber. If you wanted to, you could actually make it a little bit larger, just to make sure that you are encapsulating all the atoms that are, for example, on the other end of your calculation. That's probably not going to change things significantly in this particular case, but that's something that you have to remember. It's not the same to use the distance from the center to here, as there are more atoms on the other side, but it's not going to make too much of a difference in this particular case. So
the other thing that I might mention on that note is particularly with the SCF. It doesn't really matter in this case. It's a very fast calculation, but if the molecule were a little bit bigger, the second option after SCF, which is 0 right now, that's sort of something that's a good appropriate model for solids, and you can get a faster convergence that way. But it's a faster, if you're going to encapsulate the entire molecule, it will be faster to put a 1 there. It just changes the way it calculates things. But in this case, it's not really that much of the result should be the same. But
and this is something that people will get into as they start doing actual calculation, setting the LFMS parameter basically, and choosing between solids and molecules and so on.
So another question here is if the nanoparticle had ligands, would it be necessary to use different potentials for the core and the atoms bonded to the ligands?
Yes, actually, that's actually brings me to a completely different question. Yes, I mean, you definitely want to use different potentials for the ligands and for the atoms in the nanoparticle. But there's one more thing. If you actually look at the structure, in this particular case of this particular nanoparticle that I chose, the difference in potential from a chemical point of view between the different platinum atoms is not that big. But in a case in which you actually have differences in charging, for example, in the platinum atoms of a given nanoparticle, you definitely would want to change the potentials and not just use one clump of potential for all the atoms besides the absorber. So you would come here and you would say, for example, that the atoms that are like in this position, the ones that are like or all at 2.7, they would have a potential of 1, but the ones that are up here, they would have a potential of 2. So that would be the more correct way of doing it. One case in which that is very clear is, for example, if this nanoparticle, this is a nanoparticle floating in vacuum, right? But if you actually have this nanoparticle supported on something, right? If you actually, for example, took this bottom facet of the nanoparticle and you put it against a support, carbon, gamma lumina, whatever you want to put it on, these atoms on this facet would likely have a completely different charging than the ones that are higher up on the side, and you definitely want to use different potentials for those. So you would have to modify your input file. You would have to add a potential of 2, for example, here. Okay, so that's something that you would have to probably learn as you go along. So, are there any more questions on this?
On the nanoparticle? Did not know. The next question was about dopants, and I'm just going to answer that on the chat.
Okay. So what I'm going to do now is I'm going to go to the third one, and this one is kind of interesting, and hopefully we can complete it too. And by the way, I'm sorry, I'm actually moving kind of quickly through this. Like I said, I want to try to leave some time to see if I can get out of doing the presentation and going to Piazza and see if people have actual problems, and then look at those problems and maybe bring them back and share my screen and try to help if they are in like of general interest. Okay, so the last one is, again, you would have to make input files for these oxides, the single oxide, the mixed oxide, and the dioxide of manganese. I'm just going to use probably the input files that I have there so I don't run into any trouble with web atoms again. So the idea is going to basically run these input files and see if we can look at the position of the edge in the white line position, essentially, and try to correlate them with the Fermi level and the oxidation states that we have, and maybe partial atomic charges. This is a little bit more complicated, so I'm just going to probably do like the first part and try to just correlate the Fermi level and or the oxidation state with the position of the Fermi level with the oxidation state or the formal oxidation state. So let me start by just opening this particular case. So let's come here, and I am actually just going to copy this in this case, and just to make my life easier. So let's look at MNO, and hopefully there is an input here. So what I'm going to do is so we have an input file for MNO, and if you actually look, let's look at MNO2. There should be only one single one in here. I'm just putting everything into into an easier structure. So there are only one input file for MNO and MNO2. But if you look in this one, there should be, I'm surprised, there should be two of them. Doesn't matter. It's fine. We can, you can tell I haven't done this demo in quite a while. It's embarrassing. Okay, so we now have everything set up. So let's start with trying to run MNO just to like make my life easier. Okay. Let's try with MNO. I hate it when it does this. Okay, perfect. Let me just do a quick check here. Josh, in the meantime, maybe you want to.
Sure. No. What happened here?
I am trying to see. I'm just going to visualize it with.
Did it fail again?
No, it's. I'm trying to look at the an input file. Oh, it's why is it? Oh, why is it 0? That is so weird. There's nothing in there. So
the stuff input is.
There might be a problem. Let me just check just to see that I have everything kosher. Sorry for this.
So it might be worth going ahead and doing WebAtoms for this one because I just did CR203 based on a crystal structure and that I found online, and it seemed to work fine.
Okay, so let me take a look then and see if I can download
it seems to be something particular with that
particular one.
Structure for CR03.
Okay, so let's come here, atoms, and let's go to manganese. Let's do MNO, run WebAtoms, and nice. We're going to, yeah, this is pretty nice. There's a unique one. Let's do an 8 angstrom cluster. I don't think we need any more than that. Let's take a look. Compute. Yeah, this seems pretty reasonable. So let's save the input file. Good. So let me come here. MNO. Let's delete these two old ones. Oh, I know what's going on. Yeah, my life is so complicated. I don't know why I can't delete it really. Just give me a second. Yeah. Let me do something here just so that I don't screw up. Yeah, okay. There we go. Now we have stuff. Let's come to download. So this one should be here. So that's the MNO one that I just downloaded. So we can go to MNO2. We're going to delete these old ones. And I'm going to come back here, go to the database again, manganese, and we're going to look for MNO2. Let's just choose that one. Hopefully it's the right one. Let's choose 8 again. And you can see there's only a single one. Yes. Compute. That seems pretty reasonable. Let's save it. Now we can come here to download and move it and leave it ready there. And now we have this one, which we're going to delete the old one, and we're going to do MN203. Manganese again. MN203. Okay, so interesting thing here. You can see that there are two different manganese here, right? There is the two different sites for the manganese, and you probably should run both of them. So what we're going to do is, again, change this to 8, and we're going to save one file with the first position and a file with the second one. So let's save this one first, compute, and save it. And I'm going to come here and I'm going to take this one and put it in here. But what I'm going to do is I'm going to make another folder and I'm going to name it MN1. And I'm going to put that one in there. Now I'm going to make another folder, call it MN2. And I'm going to come here and I'm going to generate it for the other manganese. So you can change the absorber simply by doing that and recomputing. And we're going to save that input file. And we're going to move it inside MN2. So now in MN1, we should have one input file for MNO2, and then the other should have the other. So far, so good. I'm going to reopen FEFF now. And I'm going to go and do those oxides one by one. Okay, so again, you have XAS by default, but I'm going to change it to SANES. And I'm going to look at the FMS and SCF radius. The recommendation that I have was 4 and 6, so I'm going to stick to that. I'm going to put 6 here and 4 for the SCF, just to make the calculation reasonably fast. So everything I think is correct here. So let's save and run. So if we come here, you can actually see all the results starting to appear for this particular system. I'm getting there, oscillating a little bit. There you go, almost there. Wow, this takes a while. How are we doing on time? We still have 1 hour left, right? Okay, so this one finished. So that was MNO. I'm going to come now and I'm going to open MNO2, make the same changes, SANES 6 and 4, and we can save and run. Okay, so that one is done. Good. So if we look here, we should have all the results. It's done. So now we have to do 2 more. So one for the first manganese and then for the other one. So we're going to come open and the first one again, same 6, 4. Everything seems reasonable. Run it. So we should be getting results here. Yep. I feel like I have to talk during this whole thing, but I don't have much to say, right? Okay, so it's almost done. Now we're going to do the FMS, but this part shouldn't take that long. Well, maybe for this one it will. Oh, there we go. So one point that I should make is we're going to try to go and start extracting data pretty soon out of this calculations. So I'm going to basically create a file that we can take a look at. So give me a second. Yes, I'm going to just be using a text editor to collect the data that I want. So what I'm going to do is I'm going to try to associate the formal oxidation state of each one of these systems with the position of the edge, if you want, or the position of the white line. So we're going to see, and depending on what we see in the spectrum, we're going to basically try to gather some results out of that very qualitatively. There are better ways of doing this. So just for now, let's say, let's make a file called correlation in that. So what we're going to do is basically just say that MNO is going to have a formal oxidation state of +2. MN203, we're going to call it +3 because of the mixed behavior. And MNO2 is going to be +4. So this is going to be oxidation. And then we're going to put here energy of some kind, like white line or something. And I'm going to come back to this file in a little bit once we have the results. So this one finished, and this one was MN1. So now we're going to go and load file open MN2, do exactly the same thing. I'm going to do sains, I'm going to say 6, 4, and we're going to save and run it. So if we could actually go and look at the results in the plotter for the that JFEF gives you, but probably at some point you're going to want to start using your own plotting programs to actually visualize results. So what I'm going to do right now is just to use the one that I usually use, which is called XAS. It is actually a fairly nice plotting program. And what we're going to do is we're going to import the data that we have. We're going to go first for MNO. So I'm going to come and choose the xmu.dat. And I'm going to choose some very specific options. I'm going to choose which columns I want to do. This is very specific to this program, so you don't have to really worry about it. We're going to do 1 and 4, which, if you remember, are the ones that are important. So you can actually see the spectrum of MNO in this case. Now we're going to come and load MNO2. Same way. New, okay, 1, 4, accept. And I'm going to start labeling them just to make my life easier. So this one is going to be MNO. This one is MNO2. Let's change the colors. Make this one a nice blue. This one a nice red. And so we have the data for those two particular cases. So now I'm just waiting until FEFF completes. It's still running, the second MNO, but we are going to go and load anyway the of MNO2. We're going to do, sorry, the of MN203. We're going to load the first one, the MN1. So come here, do it the same way, accept. So we are going to do, this one is going to be MN203 and is the MN1. Typo, and we're going to make them green. And you can see that it's already showing in between the other one. So you have the MNO that is showing to the left, MNO 203 is in between, and then the one that is to the right is the one that has the largest oxidation state. So hopefully we can get some interesting correlations there. So is this over? Yes, it's finished. So we can go and load the second MN atom. Okay, accept. And you can see, let's make it also green, same green. Let's make it orange. And we're going to say MN203, MN2. So now what we're going to do is we're going to focus on this region. So you can actually see that, I mean, the calculations are actually fairly rough because we didn't do that much of a good job really at putting a good amount of number of points in there. But we're going to try to estimate what the position of the edge is. And what I'm going to do is I'm just going to go essentially halfway here. So let's say somewhere around there, that is giving us an energy, or if you look up on the top here, you can see the energy that I'm pointing at. That gives us an energy of about 6552. So for the MNO, let's say 6552 for the energy. Okay. For the other one, what we can do is we can estimate more or less halfway and at about here in between the two. That gives us 6554. I'm being very, very rough here for your benefit. And here we can do half, and this one is 58. So it's not going to be perfect, probably because we didn't do a majestic job at doing the calculations. But now we can simply go and just write that file, and I can close that. And I can try to plot this. You can just load correlation to that. And you can see that it's not perfect, but it's a fairly reasonable correlation between the oxidation, the formal oxidation state, and the energy of the edge. We could try to see if we could do a slightly better job by looking into the Fermi energies that FEFF actually calculated. So let's see if I can do that very, very quickly. I'm getting text messages, and I don't know if it's Josh that is trying to text me or not.
Nope, not me.
It's not you? Okay, so I can ignore them then. So, okay, so what I'm trying to do now is I'm going to go and actually look at the files with a text editor. Actually, let me just do it with Notepad. So it's a little bit more familiar to you guys than me using VI, which is a Unix editor. Let's go to MNO. And what we can do is just open the XMU of that. And we can actually find the Fermi energy, like I mentioned in my talk, And you can see that is this number over here. So I'm going to copy this, and I'm going to look at the correlation.dat file and see if I can do a slightly better job. So let's copy that for MnO2. So that is 11.58. And let's call this the Fermi energy. And now let's open the MnO2. And we have, oh, these are going to be very, very similar. Wrong one. There we go. And let's look at the other two. Exclude that. We have, obviously this is not going to work because it never does. That's for one of them. And let's go look at the other one. What I'm doing right now is actually fairly risky because the calculations that we did are not exactly the most perfect FEFF calculations. So you have to take this as a very rough approximation. So yeah. So you can see here that the correlation is not going to be as good if you look at the Fermi level. We could actually just average these two numbers, and you can see immediately that there's it doesn't really follow the same as the positions of the edge, and that's probably related to the way that we did the calculation. And sometimes it doesn't follow exactly with the Fermi level. But another option would be, like we did before, would be to look into the sorry, the position of the wide line, the intensity of the position of the most intense peak. Let me see. That will be the edge. That's the Fermi level, and let's see if we can add the wide line information in here. So these are typical things that you would do when you do research with FEFF in different materials. So the wide line for MnO, we can put it at 6557. For these ones, we can estimate more or less in between here because they have this like split peak. And that would be 6559. And the last one is at about 65 or so. So let me just compact this into a single number and call it 12. Actually, let's call it 8. So this way we have just a single number. So what I'm going to do now is I'm going to just replot the data that we gather. All the data. And of course, the Fermi level has a much larger difference. So let's just look at this region. Let's just look at the white line. And you can see that both the position of the edge and the position of the white line show more or less the same kind of behavior. Again, this is very typical what you would do when you do FEFF calculations. You could also go and compare densities of states and so on. But this is a very typical example of what would be done. Okay, so let me just save this. just to have it. Okay, so I am going to stop sharing my screen because we are at like 10:15 already, and then maybe we can see if we can answer questions and look at your actual problems.
So one of the questions was about changing the way we're running FEFF to parallel runs versus single processor runs. And there are various ways you can do this. So if you have a computer that you can install MPI on, then you can just run in parallel directly on your laptop, for example. Sometimes I do that because I have a Linux partition, but and I believe there are ways to do this with Windows as well. Now, you would need to, I'm going to open up my files here and just show you kind of where things are. So on Windows, at least, you can go to the program files, x86, and then there's JFIF. And some of you may have it in program files, not x86.
Hey, Josh, just a quick comment. The resolution that you're coming with is pretty weird to me. I basically everything looks kind of messy.
Just blurry.
Yeah, kind of blurry and with like weird colors.
Let me see if there's a share setting that I can.
I wonder if mine was kind of weird too.
It's optimized for motion and video. So, okay. So anyway, I was going to look in the program files, JFEF, and then in FEF90, there's a mod directory. So these Win32 and 64 have executables in them. Some people don't have the 64. But in mod, there's the actual source code, and there are things for compiling it. And that's the sequential source code. But if you go to MPI, then it also has the parallel source code. So you would have to ask us exactly how to compile it and everything. You kind of look and get an idea, but you need to have some kind of MPI first. So anyway, that's how you would start, is just get a machine with MPI, figure out how to compile the code, and then you would have your settings and set it to run in parallel, and then you'd give it the correct command. So this one in particular, you give it a number of processors, say it was 32 or something, and then you can also give it, if it's a machine that has multiple, if it's a high performance compute cluster, you might give it a list of different hosts, for example. But anyway, so that's one thing you can do. The other thing you can do, if you are using a high performance compute cluster, then you might want to set up SSH here, and you would SSH to another computer, and then it will run that command on the other computer. So you're going to set up your MPI command here. The one thing is, many high performance compute clusters use a queuing system, and this does not have, this isn't set up to do that. But anyway, so that's how you would set up the SSH, and then you would click on this to change to SSH. And yeah, so that's basically how you do that. I would say probably if you're going to run on a high performance compute cluster, it may be because you're wanting to run quite a lot of different calculations, and it's worth learning how to do that by the command line. You can set up automated runs. For example, if you're doing things like doping systems, then you may want to set up a script that creates an input file by random replacement, or creating random vacancies, and then runs it and creates another one and runs that. you know, and that kind of thing. And you know, JFEF isn't necessarily the most efficient way to do that. Okay, so another question was just about how to you know, go about making a FEFF input file if you already have a CIF input. So I thought we could go over, go ahead and do that, right? So you could go to, for example, crystallography open database, or there are other databases that you can look at. I'll go and see. Oh, let me go to this one here. All right. American Mineralogist also has a crystal structure database. And I'm going to search for lithium oxides. All right, so this one is Li2O2, for example. And I can download the CIF data for this. So I'll let you find your own Li2O2. You could get it from this one if you'd like, but I can save this. And then I can go to WebAtoms. And up at the top on the left, you've got a CIF input that you can use. So you can browse, grab the CIF input, and hit submit crystal data. And I'm going to do sites here so that I get a different potential for all of these different lithium and all these and both of these oxygen, right? I'll make the cluster size a little bigger. That's really not very big. Basically, the thing is, this is actually limiting the size of the actual cluster. It doesn't really necessarily have anything to do with the FMS and FDF sizes. So if you want to put this at something fairly large, it will give you lots of atoms, and you'll have plenty of atoms to try your convergence with, right? But it doesn't start, you know, you can start out your FMS size after you do this with something relatively small. So let's hit compute with that. I'm going to do the lithium edge. And okay, so that's what it looks like. I'm going to go ahead and copy this and put it where I like to run things. Okay, so one thing to note is that on some systems, if you save as FEFF.inp, it can sometimes give it the wrong line ending. I think it's mostly on Linux systems. So if you're using Linux or Mac, then you might want to just copy it. I always copy it and paste just in case. Anyway, so now I can open this. And I can view it. All right, so the situation here is kind of an interesting one for this particular system, because for lithium, you can see there are lithium that are sandwiched between these basically diatomic oxygen molecules, like this lithium here. And there are also lithium that are more or less isolated from other things, right? So those are quite different in terms of their chemical environment, and you'll want to give those different potentials when you calculate this. So that's already done. You can see this on WebAtoms. It has one potential for the absorber, that's IPOT 0, and then it has one potential for each unique lithium in the crystal system, and then it has one for each oxygen, right? Now, you can also decide not to do that, and there are reasons you might not want to do that. So if you have a very large crystal system where maybe you have slightly different, it's a big unit cell where there's slightly different oxygen positions, but the chemical environments of all the oxygens are the same, for example, then you might not really want to have them all be the same or all be different potentials. And it can be a very good approximation to just do elements, for example. And so in that case, I would compute here, and I just get the absorber potential and one potential for the lithium and one potential for the oxygen. So I'm not going to use that one this time because I think it's interesting to see how different the others are. You kind of saw that with the manganese system, but we didn't actually create it from the atom's input, I think, although I wasn't watching all of that because I was answering questions and stuff. So anyway, we can close this. Let's change this to Zanes. I'm going to put FMS at 4 because I don't want to wait for a long time. That's probably not enough, and I'm going to put FMS at 3, or FDF at 3. Okay, so, and then let's just look at what we've done here in terms of the lithium. I've put this on lithium 1, right? But there's 3 different lithium. So we can, I'm going to actually go ahead and save this as a different file. Let's see. Oops. All right, I'm just going to go ahead and run it. All right, so, and then while it's running, I'm going to create a new directory for the other lithium 2 and 3. New folder, and another new folder. And I believe one of these lithium is very similar to the other, and one of them is quite different. So I can copy the FEFF input file into each of those directories. Actually, I don't really want to do that. I'm going to delete that, and when it's done, then I'll change things and save it in those directories. Okay, so it's done. I'll just plot it to make sure I actually have something in there. Yes, it seems to have calculated things. Great. And that is the lithium K edge. That's okay. All right, so now let's decide we're going to change our absorbing atom. And again, I'm going to view this just to see where it put my absorbing atom in the first place. You can see it's the pink atom right in the middle. All right. So now we want to edit and change that absorbing atom. I'm going to change this. Let me see. Li1 has the potential index 1. So I want to change this this absorbing atom to the potential 1, and then I want to change. We'll do the lithium 2 next if it's here. Where is lithium 2? There's Li2. That's the first Li2, and so I'm going to change that one to 0, and then I'll save it. And I'm going to save this again in the directory Li2 that I made. Oops, I saved it in the wrong place. Li2. So let's save, and then I'll view it just to see where my atom is again. Okay, so now it's a little closer to the edge of the structure, but it's probably close enough or far enough into the structure that it's okay. If you're worried about that, you can always create a bigger structure so that you don't have to worry about it being, not so close to the center. Or you can recreate it from web atoms with it in the center, with that particular lithium in the center. Okay, so let's go ahead and hit save and run again. While I'm doing that, I'm just going to look at the chat to see what's going on. Okay. All right. Okay, so that one's done. I'm going to go ahead and plot both of them together. So here is I'm going to make this a different color. All right, so there's the new calculation. Let me just make sure that's the right thing. Li2, good. All right. And then I can open another file here. And those look almost identical, if not exactly identical. So probably this one is not particularly different in terms of its structure. So let's calculate one more. So we want to open, oh, actually, cancel. We want to edit the atoms again, and I will change again this potential. I'm going to put it back to 2 because that's the Li2. And then I'll go up to the top and find the first lithium 3 and change that to 0. So now I have lithium 3 as my absorbing atom. And I'll save it again in the document, the Li3 directory, and hit save and run, and see what this one gives us. So you can see that because the absorption of the Li1 and Li2 are nearly identical, probably the densities around them are nearly identical as well, or at least the spherical densities, which is what we use. And so you could probably get away with only having one potential for those two lithium types. And then, well, we'll see if this one's different. Okay, so now let's plot this one. Okay, clearly this one is different than the other one. Okay, so let's open up the other one again. All right, so and I'll make one of them a clearly different color, and maybe make this one dark blue or dark red or something so you can see it a little better. Okay, so these are clearly different. So the lithium 1 and lithium 2 are fairly similar, and lithium 3, or they're almost identical in terms of the absorption, and that means the electronic structure is almost identical. And again, therefore, you could use the same potential for those two, and that's important just because as you add more and more potentials, having 5 or 10 is fine. But if you get to where you're looking at like 60 different potentials, maybe you have a very large molecule or something with lots of different oxygens in it, you don't want to have that many. So you want to start thinking, well, which ones are really going to matter for the absorption that I have? So you can do something similar to what you're doing with convergence of FMS and SDS, where you start adding unique potentials around the absorber, right? So if you have some oxygen that's right next to the absorber, say it's a metal with ligands on it, and then the ligands are quite large and have lots of different oxygens in them. You want to represent the oxygens next to the absorber pretty well. You don't really care so much about the ones that are out further. Okay, so that's pretty much it for that demonstration. I'm trying to think of if there's anything else that you want to do for now. I think we went through all the examples, yeah? You wanted to do a demo, right?
Well, there was just one question about averaging, and I thought I would point out a couple of things for people that want to do averages, just so they are aware of a little bit of the caveats involved in doing averages.
Right.
So yeah,
let's bring this back up so you can. Are you talking about averages over different sites, or just generally averages?
Well, the question was about MN1, the case of manganese 1 and 2. So let me just show the screen because I have the plots already. Remember, I made them.
Yeah.
Sure. So I just want to show what might be like. I mean, the grid issues, for example, for averages. So let me see. So you should be seeing my screen now. This is a plot that I made earlier for the manganese cases, and you can see that we have the manganese Mn2O3 that had two different manganeses. So I'm going to basically hide the other two cases, and I'm just going to keep these two on the screen. First of all, I just want to look at I want to show you something about the data. So if I double click, this is going to bring the two grids that are used in the calculation. You can see that the X grids are different. They are slightly shifted. So they do have the same number of points. They have 100 points. But if you actually were to do the average the way that you would normally do, which is basically assume that you have the same value of X and then just average the values of Y, which is the way that you would be doing it, you would run into trouble in some cases. I mean, in this case, it wouldn't be too awful because the energy grids are not that different, but there might be differences in the energy grid. So this is something that you have to keep in mind when you want to do averages. So the way to do it usually is to take your data, spline it into the same grid, and then do the averages. I mean, I'm just going to do the example here, and this software actually has a way of doing this fairly simply. So I just basically choose interpolation splines, and I'm going to spline these two things into two different grids, and I'm going to just choose the grids to go from like 6530 to 6700. So 6530 to 6700. And I'm going to just I'm just going to interpolate a little bit and just basically do 200 points. And you can see that the curves are almost identical now on top of each other. They have a little bit more data. So I'm going to hide those two. So these are the ones that I just interpolated. And now if we look at the grids, you will see that they have the same energy grid. They have exactly the same energy grid. So now you can actually, you would be able to do an average between these two things. You can use whatever program you want. Mathematica can do it. There's a bunch of plotting programs that do it. In this case, what I would do is I would just basically take these two sets and just do an average of them. You can do it with this basically calculator feature that it has. 5 dot y, and this should essentially generate something that is essentially the average of the two. You can see that there's a curve that appeared in the middle between the two, and that's just the average. I mean, basically the crossing points are the same. There are many ways of doing this, and my recommendation is that you find the tool that you think is the easiest. Unless, Josh, do you have anything that you recommend that for general of people to use in general that can do this type of averages?
comment on that. You can, in principle, use the large that Matt knew.
Oh, there you go. Yes, large can do it. Yes. Yeah.
Yeah, I don't have anything in, I mean, there's stuff, you know, if you like Python, then there's lots of stuff to do it there. But yeah. There is, I don't know if you already mentioned this, you might have already mentioned this, but did you say anything about the absolute card?
Oh, no, I did not mention
That's
that.
also important for
Yeah, that is
averaging.
something that is, that is something that is actually, let me share again. That is something that is actually kind of important. And I just glossed over it. Just give me a second. Let me find this thing. Let me share again. So these calculations that were done, I mean, FEFF basically took the results and normalized them in an interesting way that FEFF has for doing normalizations. What it does, it takes the energy, that it takes the intensity 50 eV is above the edge, and it basically sets it to 1, and it basically rescales the whole spectrum, so the intensity at 50 eV above the edge is essentially 1. You can actually get absolute results in FEFF if you use the absolute card, and that's actually going to give you exactly the relative intensities between two different cases. And that is something that you probably want to do when you do averages. You want to do the averages on absolute absorption instead of this relatively normalized one that FEFF has. In this particular case, the normalization factors are probably very similar, and we can try to take a look at that. So let me see if I have the results here. I can probably find it out very quickly. So if you go to MN1 and you open the xmu.dat, and let's just leave it there, and let's go to the MN2, and we open the xmu.dat for MN2. You can see that it actually tells you the normalization factor. See, it says x edge plus 50, and the normalization factor is 3.48, blah, 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 times 10 to the minus 4. So if you multiply your results by this number, you get absolute units. And you can see that this one, in this case, is 3.50. So in this particular case, you can actually do those average without really that much trouble. But there are certain cases in which the normalization factors are slightly different between the two cases, and you actually want to have them exactly the same. So your two options are either you run your calculations with the absolute card and get results in absolute units, or you do your calculations and you get normalized results, and before you do the averaging, you take into account the normalization factors, just basically by multiplying your intensities by these numbers before you do your averaging. So that's a way to do it. Thanks for reminding me of that, Josh.
One other thing on the averaging over sites and that kind of thing, of course, you do want to be careful that you're averaging and weighting by the correct stoichiometry of the system.
Precisely, and I mentioned that when I was going over the platinum nanoparticle case. I mean, you always have to average with the proper stoichiometry, and either you use the stoichiometry of your crystal, or in the case of the nanoparticle, you count your atoms in there, and you use the proper number of atoms just to get the multiplicity. There's a question here that probably is more for you than me, Josh. I mean, it's basically averaging for XAS fitting. And I don't know if people do a lot of averaging of XAS of this type for different sites for doing XAS fitting. Is it something? Yeah.
I don't think it's not normal for people to really do averaging outside of the fitting. Sometimes when you have, for example, two very different, chemical species that are both contributing to the K edge, for example, you'll calculate the paths from both of those, and then you'll add a path from each one of them, right? And then
Yeah.
you fit both of those, and you may know the coordination of each path, for example, and fit the bond length. And obviously, same as any XAS analysis, you want to pare down the number of free parameters as much as possible. And all of the details about how you do that stuff, there's probably a question for Matt, but or the other people here more than me.
Yeah.
But yeah, that's the kind of thing that you would do rather than averaging the output of FEFF first.
Yeah, definitely. So maybe we should have more questions now and see, I mean, we've been trying to answer as many as we can. I don't know if we missed any. Maybe if we missed something, people can put the question again right now, and we can try to see if in this last 10 minutes or so that we have.
Could you touch a little on the print option for different cards? Because depending on the
I couldn't understand. Sorry, I couldn't understand what you said. On the what?
on the print card.
Oh, the print card.
Yeah, so depending on print, there may be different output options, and then some files are only produced with a certain print value.
Yes, I mean, Josh probably is the best one to answer this. I mean, but I mean, the default one is going to produce the vast majority of the files that you are interested in looking at. If you're interested in producing something like maybe atomic potentials or a more detailed printout of all the sanes, all the XAS paths and so on. You just
for instance, the XAS paths.
So that particular one, I think it's the very last. It's the print statement for the spectrum. Let me share my screen really quick, and then I'll just show what. I don't know if we went over this already, but if you click on Tools and Help, then you can move your mouse over.
Oh, I forgot to mention that.
And so this is always, something good to be able to figure out what different things are. In this particular case, okay, it's 0 for each module. That's not very. But so anyway, this last one, 3, this is a print card, but in JFEF, you actually choose different modules and then go and choose the print level. And the cross section is actually what you would choose 3 on to get your XAS parameters. And then there are lots of different files that you can get from all these different print levels here. So if you put it up to 5 on potentials, then you get atomic potentials before and after the SDF, and some other things as well. I probably wouldn't be able to just list them all off. For phase shift, I think, I don't even know what all of them are for phase shifts. I think there are some of them that give phase shifts out as text files, for example, rather than just, right now it's output, by default it's output as binary. Just a note, if you put it to 3 on phase shifts, it does a different type of calculation and it takes much longer. So it's a little bit misleading. It calculates Mulliken counts, which could be useful, but it does a whole, usually the phase shifts take about, 10, 15 seconds at most. And if you put it on 3, it will do a full multiple scattering calculation. So it may take an hour, depending on how big the system is. Otherwise, I don't, the other things that we have in here, I haven't used them all that much, to tell you the truth, the different print levels. It's mostly just cross sections when you need those FEFF NNN.dat files, and things like the potentials here. But if you look in the documentation, it will explain the print level for each one of them. But generally, okay, the help tool is pretty good about most of these different things. Oh,
Josh,
go ahead. Yeah.
Since you're there, I mean, there's a question in the chat that basically somebody missed the way of doing the normalization. So I thought maybe you can show the absolute.
Yeah, sure.
Thing right there now.
Setting cross. There it is. So if you click on cross sections here, you can click absolute.
And that is going to give you
absolute units in the output.
Exactly, and the xmu of that. So if you do not have that click when you do your calculation, you have to you go into the xmu of that and read the normalization factor, and remember to use the normalization factor when you do your averages. But if you do your calculations with this absolute thing clicked, then you can just basically go and do your averagings without worrying about having different normalization factors in your calculation, because the calculations are going to be absolute. Awesome. So I think that answers. There's another question. That this one is a historical question about why WebAtoms has FEFF6 and FEFF8 options for input, but not FEFF7.
Not FEFF7. Well,
FEFF7 was like an intermediate step, a version of FEFF, a stepping point, and it was never really used that much in public, right, Josh?
That's right.
It was never distributed so
not very much.
Yeah, not very much. And the main important thing is that the input styles of FEFF can be classified into two styles, the FEFF6 style and the FEFF8 style. So if you're going to be running FEFF9 or FEFF10 or whatever, you're going to be using the FEFF8 style of input. Everything else is going to be using the FEFF6 style of input, which is the original one. So that's for the point of view of WebAtom, that is the main difference in there between FEFF6 and FEFF8.
There are also free versions of, FEFF6 is itself free, and FEFF8 has a light version that's free as well. So for XAS, those two are the important ones, I think. Although there are some codes, some analysis codes that require FEFF7.
They are?
I think there's one analysis. I shouldn't say some. I think there's just one. There's some kind of output that is used in FEFF7, or that it's printed out in FEFF7 that for some reason we stopped printing out, or it changed or something. And so
interesting. So in the last few minutes, any more questions? So doesn't seem to be anything else, but somebody earlier was asking about the Weibuller factors in ab initio, the Weibuller factors and how to use them and so on. And it's a very hard question, and so what I did is I tried to answer as much as possible in the Piazza thread that I started. And ideally, this is something that I would like to take offline. And if the person that was interested in this wants to continue the discussion in Piazza, and actually they want to show me structures and so on, I might be able to help them with a little bit more detail and guide them through the use of that. I mean, the use of the ab initio, the Weibuller factor, is very much an expert option in FEFF. It has been simplified, but it has so many complications from the fact that you have to input data from stuff that is not FEFF. That kind of complicates things significantly for a lot of people. So anyway, that's it for me at least.
Just a short question. If our participants have some question popping up after this session is closed, can they contact you by email or in the Piazza classroom, or where? How to get help from you when people come get into trouble with that?
Oh, Josh unmuted himself. Yeah. Usually we are available for helping after the demos for some time. I mean, they can just send us questions and they can basically start a discussion with us, and we will try to help people as much as we can.
There is also a contact inquiry system set up on the FEFF website, which is
the official way to contact us.
FEFF-project.org, I believe. Yeah, there it is. Okay. So anyway, if you go to code FEFF9, I think that's contact. So contact us, and you can put in stuff here and ask a question. Usually people contact us on this about, wanting to buy FEFF, but it would be fine to ask. This goes to all the developers. So.
Yeah, so if there's no more questions, right, then thank you. Thanks a lot. Yeah, I already mentioned this in the morning. Too bad I didn't see those videos and these demos 15 years ago when I was writing my thesis. But for many people, I'm sure it was a very useful experience today. So thanks again. I remind everyone that it's still okay to ask your questions regarding FEFF on Piazza Classroom. And our next meeting will be in a week, the next Friday, November 20th, and usually we'll be presenting his FDM scope. So thank you all, and have a good rest of the day.
Okay,
Bye.
Thank you very much for everybody.
Thank you.
Okay, bye.